Hello everyone, I'm Mahnur and today we will be diving into the yearly past paper for AS and A level physics, specifically paper 1, variant number 2 for the tenure May-Jun 2023. So let us begin. So here we have the first question. A stone sinks in water. What is a possible value for the density of the stone? So this is the kind of question where you're not expected to memorize any such value for the density of the stone, but you should be able to compare the values that are given. Since the stone is sinking in water, that implies that the stone is more dense than water. What we should remember is that the density of water is roughly around the power 10 raised to the power 3. And we can even assume it's 1 into 10 raised to the power 3 kg per meter cube. In which case we can cancel out option A first and foremost, because if we notice, here we have the case where it's of the order 10 raised to the power 2, which is actually less than that of water. So we can cancel out A. And in contrast, we can cancel out option D as well, because although this value is greater than the value of the order 10 raised to the power 3, it seems to be an unusually high number when it comes to a smaller stone. So we can cancel D as well. So we're left with B or C. Even among these two, we wish to choose a number that's larger than the approximate density of water, but not too large where it's of the order 8 into 10 raised to the power 3. So even C can be disregarded as a value being a bit too large, and so the best option we have is option B. Now on to question 2. Gigameters, terameters, micrometers and picometers are all units of length. Which unit is the largest and which unit is the smallest? So here's just a matter of recalling the values of each of these prefixes. So if you recall, for giga, the value is 10 raised to the power 9. For tera, it's 10 raised to the power 12. Micro is 10 raised to the power minus 6. And then finally, pico is 10 raised to the power minus 12. So we can clearly see that of these four, tera is the largest, while pico happens to be the smallest. So under this scenario, the best option that we can pick is option D. Great, let's move to the next one then. Now here we have the following. An aircraft travels along a horizontal path. Two of the forces that act horizontally on the aircraft are the thrust force of the engines and the force due to the wind. The vector diagram for these forces is shown. Which vector represents the resultant horizontal force acting on the aircraft due to these two forces? Now, here it's a matter of recognizing that since you have two forces, the thrust force, I'll call this T, and the force due to the wind, I'll call this F. Both these forces are arranged at an angle with respect to each other. So if I wish to combine them in some way, I'll have to do that using the head-to-tail rule. This is basically that way of adding two vectors together such that you take your first vector of the two. Let's say we pick F. So I'll draw it in a way that I don't change its magnitude or direction. So let's say this is F. And now I draw the thrust force T in a way that its tail must join the head of the first vector that I've placed. So let me draw that as so. Make it a bit neater. Like so. So roughly speaking, this is the closest we can get, right? And now you basically have to draw the resultant vector, which would simply be drawn starting from the tail of the first vector drawn, and it will be directed towards the head of the second vector that you have drawn. So this red vector that I've drawn is my resultant force. So the one option that matches the red vector that I've drawn here happens to be option C. So that is my answer, right? Now on to the next one. Here we have question 5. A ball travels from point X to point Y along a semicircular track of radius 1 meter as shown. What is the displacement of the ball from X to Y? Now, this is a matter of displacement, and we recall that it's basically the shortest path starting from some point x directed towards point y. So the displacement we wish to measure is basically in this particular fashion. Now you can see how the red line that I've drawn here is nothing but the diameter of this semicircular path that we see over here. So the diameter can be calculated since I know what the radius is, so it would just be 1 plus 1. So this whole magnitude of displacement, I'll write that with S, equals 2 meters. So I can at least cancel out options C and D since they don't match the 2 meters I expect. And now we remind ourselves that since this is displacement, it's a vector quantity. And if it's a vector, it should have a magnitude and a direction. So even though we might be inclined to directly and quickly pick option A since it matches the 2 meters, it's not a complete answer because displacement requires you to specify direction as well. And since our arrow is pointing downwards or in the southern direction, it makes sense that option B works very well over here, right? Now on to the next one. Here we have question 6. A rock is launched vertically upwards from the surface of the Earth and an identical rock is launched vertically upwards from the surface of Mars. Each rock is launched with an initial velocity of 12 meters per second. Each rock then reaches its maximum height above the surface before returning back down to the surface. The velocity time graph for each rock is shown. In both cases, air resistance is negligible. Now they ask, what is the difference in the maximum heights of the two rocks? So this question basically revolves around the concept of free fall, specifically free fall on Earth and then on Mars. And now we wish to understand or remind ourselves or in fact calculate what the difference in the maximum heights are. Now this requires us to figure out what the maximum heights for each of the rocks on Earth and Mars is. For this, we recall the fact that when it comes to maximum height, that is achieved when the rock momentarily stops in midair, because once it stops, only then can it not go beyond that and achieve an even higher height, right? So at maximum height, the final velocity, even if for a moment, is 0. So we wish to locate points for both the Earth graph and the Mars graph wherein we have velocity that has started from 12 meters per second right here, but then stops at 0, which would be right here. So for the Earth, that would be up to this point, and then for Mars, it would be up to this point. Now when it comes to actually computing this maximum height, this is nothing but a form of displacement, in which case we remind ourselves that for a velocity time graph, the area underneath the graph line represents displacement. So up to the points that I've marked off for both Earth and Mars, we can basically find the area underneath the graph line to figure out the maximum heights. So in this case for Earth, it would be something like this region. And then for Mars, it would be this region. So we can see how it's a larger triangle for Mars and a smaller triangle for Earth. Let me just mark it off separately for the Earth, like so. So now that we have these two regions, now it's just a matter of figuring out or calculating values of these areas. There, of course, we can see that they're triangles. So it would just be an application of the formula for the area of the triangle. So for the Earth, we could do half times base times height of that green triangle right here. The height is 12 meters per second. And the base can be, basically we have to break down the calibration given. So since we have 10 small boxes that represent 2 units, each unit is split into 0.2 seconds. So 0.2, 0.4, 0.6, 0.8, 1, and then 1.2. So calculating this should give us exactly 7.2 meters. Now let's do the same for Mars. Once again, the same formula, half times. Now the base here would go beyond 2 seconds. So 2, 2.2, 2.4, 2.6, 2.8, 3, 3.2. And then the height is still the same, 12 meters per second. And now once again, we calculate it and we get 19.2 meters. So now that you have both maximum heights, now it's just a matter of finding the difference in height, delta H, which would be 19.2 minus 7.2, and what you get is exactly 12 meters. And so our final answer is A, right? On to the next one. Here we have which statement describes the mass of an object. A. Now here's just a matter of picking which option makes the most sense. Now here, a quick way to solve this would be reminding ourselves that mass is a scalar quantity. So it only really has a magnitude and no direction. We can immediately cancel out options A and B because force and momentum both are vector quantities that have a particular direction to them. Mass in that sense is not the same thing, so A and B cancel out. Now, if you use the same line of reasoning, you might be inclined to ignore C as well, because when we hear the word resistance, we might think of any resistive force. But for option C, we should be a bit more careful and read the entire statement. It says, the resistance of the object to changes in motion. This is basically referring to the ability of an object to resist any changes in its motion, which we remind ourselves is actually a property of inertia. And from a discussion of inertia, you might remember further that mass in that regard is a physical manifestation of that inertia, or it's a physical way of understanding what inertia is, right? You might remember that from recalling that mass and inertia were directly proportional to each other. So they're quite interlinked with each other. In that sense, option C is pretty much a good option. And just to be sure that C could be the correct answer, if you look at D, it refers to weight, which in itself is once again a force, it being a vector. So while yes, mass might have something to do with the balance, it's not really the weight, because in physics they're very different things. So the only best option we have is C. Now we have question 8. A submarine of total mass 3200 kilograms is at rest underwater. The total mass of the submarine is suddenly decreased by 200 kilograms by pumping water out of the submarine horizontally in a negligible time. The upthrust acting on the submarine is unchanged. The change in the total weight of the submarine causes it to accelerate vertically upwards. What is the initial upward acceleration of the submarine? Now, here it's a matter of knowing what forces are acting on the submarine while it's accelerating vertically upwards. If you look at just the vertical forces, there would be the weight that would act vertically downwards. And then you have the upthrust that would act vertically upwards. So something like this. Now, in this situation, we should first calculate the upthrust and then we can work towards what the weight is. Now, in this situation, we're told that even if the submarine's mass changes, the upthrust doesn't change. So the upthrust is created when that submarine is at rest underwater with the original mass of 3200 kilograms. Here we remind ourselves that numerically speaking, the upthrust is equal to the weight of the amount of water displaced. Right? In which case, the submarine is displacing about 3200 kilograms worth of water. So the weight exerted, or the weight of that water would just be calculated by m times gravitational acceleration g. So the upthrust can be figured out by that original mass, 3200 times 9.81, and what we get is the following. We have 31,392 newtons. Now comes the point about the new weight. We consider new weight because the total mass decreases by 200 kilograms. So the new mass, m, is now 3200 minus 200, giving you 3000 kilograms. And using this, we can calculate the new weight of the submarine, which would be 3000 times 9.81. And what we get is 29,430 newtons. So now we can figure out what that resultant force is due to these difference of these two different vertical forces. 31,392 minus 29,430. This gives us 1,962 newtons. Now we have to use this resultant force to calculate the initial upwards acceleration, in which case we can use Newton's second law, which states that the resultant force is equal to mass times acceleration, which means acceleration would be the resultant force divided by mass. We have the resultant force. The mass would be the new mass that we consider after the 200 kilograms have been removed, so 3000. And what you get is 0.654 meters per second square. And fortunately, we have option B that matches this perfectly. Great. Let's look at the next question. A box in air slides with increasing speed down a rough slope from point P to point Q. The slope surface exerts a constant frictional force on the box. As the box moves from P to Q, there are changes to the magnitudes of its acceleration and the total resistive force acting on it. Which row describes the changes? Now, here too, it helps to first draw out the forces that are acting on this box, specifically forces along the plane, since the motion itself is along the plane. Now, going from P to Q, we're told that there's a constant frictional force, right? So that would act, since the box is sliding down from P to Q in this particular direction, this would imply that the frictional force must be acting in the opposite direction like this. Now, apart from the frictional force, there's also some kind of a driving force that's causing the box to slide down. That would act downwards like this. Now, since we're not applying this external force ourselves, this is arriving primarily due to the weight of the object, specifically the box. Now, you might be wondering that weight should act vertically downward. So what component is this? Well, this can be figured out from the fact that you have basically the box placed at an angle. So when it's placed at an angle, you have basically two components of weight. You have the component of weight that's perpendicular to the plane, and then you have a component that's parallel. So it's W sine theta that would be going along the plane and which is actually driving this box from P to Q, and where W, remember, is the weight of the object. So we're just keeping these in mind, and now we address the options. We want to see that the acceleration is changing somehow and the total resistive force. Now, here we remind ourselves that friction is a quantity that is related a lot with how fast the object is moving. So, the more it slides down, the larger the frictional force becomes. Because here, notice how there is not just friction, which happens to be constant, but there's also, of course, some air resistance that could act on this object as well. That's what they mean by total resistive force, which involves friction and air resistance, represented by capital R. Now, while friction stays constant, what isn't constant is the air resistance. Air resistance is something that is proportional to the velocity of the object. So the faster it moves, the larger the value of air resistance becomes. So in that sense, the magnitude of the total resistive force continues to increase as the box goes from P to Q. So we can cancel out options A and B. So we're left instead with C and D. Now, when it comes to seeing how the acceleration changes, that depends entirely on the resultant force. Now that resultant force is calculated by W sine theta, which is the driving force, minus the forces that oppose this driving force, which is friction plus air resistance. Clearly, we can see that this sum of total resistive force, this continues to increase as the air resistance increases, right? Because the total resistive force continues to increase. That will ultimately cause this resultant force to decrease. And in accordance with Newton's second law, if the resultant force decreases, then we expect the acceleration to decrease as well. So the magnitude of acceleration decreases and we're left with option D. Now on to the next one. Now here we have two balls x and y approach each other along the same straight line and collide. The collision is perfectly elastic. Their initial speeds are ux and uy respectively. After the collision, they move apart with speeds vx and vy respectively. Their directions are shown. So before the two objects x and y approach each other, and afterwards they move away. Which equation is correct? Now here we're told that this collision is perfectly elastic, and you might be inclined to manually start solving this by assuming that these two balls have the same mass. But here we have to be a bit careful because they haven't explicitly mentioned that. They're just talking about two balls, not two identical balls. So even if we might wish to treat them in the same way, it might not work. At least that's not a safe bet. What is a safe bet is a property of perfectly elastic collisions. That is, and I'll write it down here, that the relative speed of approach equals the relative speed of separation. So here it's just a matter of calculating the relative speed before they collide and equating it with the relative speed after their collision. Before they collide, the relative speed will be an addition since the objects are moving in opposite directions. And then when they're separating, here too we consider the fact that they're moving in opposite directions, and so we add them here too. So this is a good technique of directly getting the answer you want, and so your answer will be option A. Here's question 11. A rod is pivoted at point O. A force F is applied to the rod at point W as shown. What is the moment of the force F about O? Now here we recall the very specific definition of the moment, which was, it's the force itself times the perpendicular distance between the force F and the pivot. So we have the force F given already in all the options, so it's just a matter of figuring out what the perpendicular distance is. So the way we find this is in a step-by-step approach. This helps for students for those students who find it difficult to locate this perpendicular distance. So take it in as a step-by-step approach. First, you should always extend a dotted line through the force that's given. What you're doing here is drawing what we call the force arm, or the line of action of the force. Now you draw a line parallel to this force arm, but this time through the pivot. So it would look something like this. A parallel line drawn through the pivot. Now it's just a matter of locating that special perpendicular distance between the pivot and the force arm. And we locate that to be the line or the distance OY. The best option that matches this is B. On to the next one. Here it says, a uniform rod XY of weight 10 newtons is freely hinged to a wall at X. It is held horizontal by a force F acting from Y at an angle of 30 degrees to the horizontal as shown. What is the value of F? Now, here it's a matter of basically resolving the force F into its horizontal and vertical components, and then seeing which of the two components is being balanced out by the 10 newtons given here. Now, let's focus on resolving that force F. Now, force F itself is tilted at an angle of 30 degrees, right? So, we can break it down into its component adjacent to the angle 30, which would be F cos 30 degrees. And then a component that is opposite to this angle of 30 degrees, which would be F sine 30. Now we can see that the 10 Newton is being balanced out by F sine 30. And by balancing, what that means is the force acting upwards, F sine 30, equals the force acting downwards, 10. So now it's just a matter of making F the subject of the formula, 10 divided by sine 30. And what you get in the end is specifically 20 newtons. So your answer here will be 20 newtons. Now on to the next one. Here we have the next question. Two solid cubes X and Y are made of material of the same density. cube x has twice the mass of cube y, cube x has sides of length x, and cube y has sides of length y. What is the ratio x over y? So here it's a matter of relating both solid cubes x and y with the fact that they have the same density. So that would look something like this. Density of x equals density of y. Now we can go to the next step and plug in the definition of density, which is mass per unit volume, right? So for x, that would be mass of x divided by volume of x. For y, it would be mass of y divided by volume of y. Now we're told about the mass that cube x has twice the mass of cube y. So if y has a mass m, x has a mass twice of that. So we can plug in these values here. For x, that's 2m. And for y, that would be m. Now we can resolve the volumes of cube x and cube y by recalling that the volume of x will be x cube, and for y, that would be y cube. Now it's simply resolving our expression by dividing on both sides m. That causes m to cancel out. 2 over x cube equals 1 over y cube. Now we make x over y the subject of the formula. For this, I'll have to multiply on both sides x cube. And to get rid of this cube root, the cube itself, I can take a cube root on both sides. And so I get x over y, which if we plug in the value in our calculator, we should get exactly, it's in fact in the calculator you'll get it as 1.2599. That rounds off to 1.26. So your answer will be A. Now to the next one. A U-shaped glass tube contains liquid of density 2000 kg per meter cube as shown. What is the difference in pressure due to the liquid between levels P and Q? Now to find this difference in pressure, we remind ourselves that the liquid between levels P and Q, they will exert a pressure at the very bottom due to these columns of height 10 centimeters and 6 centimeters. Now this difference in pressure can be found by simply calculating what the pressure is due to P, the liquid level P, minus the pressure due to the liquid level at Q. Now for P, here we will basically recall that the pressure due to a liquid column is simply the density times gravitational acceleration times height. So for P, that would be rho g hp, which is equal to 10 centimeters. And for Q, that will be rho g hq, where 6 centimeters is the value given for hq. They both share the same density because it's the same liquid density that's being filled in the tube. G is of course the same constant. So when computing delta P, I can basically take rho and G both as a common factor, and I get HP minus HQ, which is just a difference in height. So now I can just directly plug in all my values. For density, that's 2000. For G, I know that's 9.81. The difference in height will be 10 minus 6, which is 4 centimeters. But I have to be careful and convert my units to meters if I want my answer to be in the SI unit of pascals. That would require me to plug in the value for centi, that is 10 raised to the power negative 2. And now it's just a matter of plugging everything into your calculator. And you get 784.8 pascals, which if you still round this off to two significant figures, you get 780 pascals. So the best option is A. Now on to the next one. Now we have a steam turbine is used to drive a generator. This is question 15. The input power to the turbine is Pi and the output power is Po. The power loss in the turbine is PL as shown. What is the efficiency of the turbine? Here is just a matter of recalling the definition of efficiency, which is the input power divided by the output power. Input power is given, in fact, my bad there. This should be the other way around. So let me rewrite this. We know efficiency is the output power or the useful power divided by the input power. The output power is given as PO and the input power is given as PI. The only option that directly matches this is D. Now on to 16. A variable force is applied to ensure that a constant power is supplied to a train. Which graph best shows the variation of the force F applied with the velocity V of the train? The one equation that relates pressure, power, force and velocity with each other is the other form of power, which is force applied times constant velocity of the train. But in this situation, it's not a constant velocity, but rather we wish to find the relation between force and velocity if power is kept constant. So you might remember that there's always a technique where you can get rid of a constant value or a constant term and that basically helps you see how two quantities are related with each other. So to approach that, let's first make one of F or V the subject of the formula. Since F is on the y-axis, let's make F the subject of the formula. So if I divide V on both sides, I get. Now, in order to remove this power P and the equality sign, I can, since power P is the constant value provided here, I can replace these with a proportionality sign and I get this. What this shows is that force and velocity are inversely proportional. And the only shape that matches this relation is option A, where you show that if force increases, the velocity will decrease and vice versa. So option A works best. Now question 17 states, a block is released from rest and slides a distance x down a straight slope. The slope is at an angle theta to the horizontal. The slope is frictionless and air resistance is negligible. The acceleration of free fall is g. Which expression gives the final speed of the block? Now, since there is no air resistance or any friction, this means that the resultant force will be constant. And you might remember that in the previous question I had just done, that force itself can be, that driving force specifically, the one that you see here drawn on the block, this is this is provided due to the one component of the weight. So I'll basically draw the same kind of diagram I had done in a previous MCQ, where this block resting on this inclined slope has a weight acting vertically downwards. And because of the inclination, you have two components of weight where one of it is perpendicular to the plane. That's W cos theta. And then you have one that's adjacent to the plane or parallel to the plane. That is W sin theta. And you can see how W sin theta is the one responsible for the block sliding down. So we realize that not only is the resultant force constant, but it's also equal to W sin theta. The resultant force can be resolved using Newton's second law as m times a, mass times acceleration, while weight is mg, and we can rewrite the sin theta as it is. And now we find upon cancellation that the acceleration that the box feels is equal to a equals g sin theta. And it's this acceleration that is constant. And we immediately remember that, okay, where acceleration is constant, I can use one of the Szilard equations. Now, which one we use depends on what we have and what we need to find. What we have is the fact that the box is released from rest, so the initial velocity will be 0. We need to find the final velocity, so that's our question mark placed here. We have the displacement written as x, and we know the acceleration as g sin theta. We don't really know anything else about time, for example. The one equation that relates these four terms is 2as equals v square minus u square. Plugging in all my values, I get 2g sin theta times x equals v square. If I take a square root on both sides, I get v as 2gx sin theta with a square root. The one option that matches this is option B. Now on to the next one. Now question 18 says, what is meant by the spring constant of a spring? So this is in relation to Hooke's law, which states that force or load applied to a spring is directly proportional to its extension. And if you remove the proportionality sign, you can replace it with an equality sign and a constant. And K is that spring constant we had, which shows from a rearrangement that spring constant is force applied per unit extension. Per unit implies a division. So the one option that matches this is D. Now on to question 19. A child holds a thin metal wire that is attached to a kite. The graph shows how the extension of the wire varies with its tension. A gust of wind increases the tension from 100 newtons to 150 newtons. So in accordance with the graph, that causes the extension to go from 0.3 to 0.45 millimeters. What is the change in the elastic potential energy of the wire caused by the gust of wind? Here we remind ourselves that for a tension versus tension or force versus extension graph, the area under the graph line represents this elastic potential energy or strain energy. It's the same thing. Now we wish to find the change in the elastic potential energy. Now this change is occurring because the extension is changing from 0.3 to 0.45, which means that the area that we're interested in is not the entire shaded region, but rather specifically this trapezium that I'm highlighting here. So with this in mind, it's just a matter of finding the area of this trapezium and we can figure out what the elastic potential energy is. Now for a trapezium, we remind ourselves that it's half times sum of parallel sides of the trapezium times its height. The parallel sides given are the lengths 100 and 150 newtons. So we get 100 plus 150. The height is basically this perpendicular distance between the two parallel sides, which is 0.45 minus 0.3, giving you 0.15 millimeters. But we have to be careful and convert this to meters if I want or in fact, we would have converted it to meters if our answers were in joules. But notice how they're all in millijoules. So here, fortunately, I can get away with keeping the millimeter here. So just for this question, since all my options are in millijoules, I can keep with the milli prefix. And it should give my answer pretty directly. So now it's just a matter of plugging it in. And we get our value directly, 18.75 millijoules, which rounds off to 19 millijoules up to two significant figures. So our answer is B. Now let's move to the next one. Question 20 says, a microphone detects a sound wave. The microphone is connected to a cathode ray oscilloscope, CRO. The shape of the trace on the screen of the CRO is shown. Which property of the sound wave can be determined by using only the measurement of a horizontal distance on the screen and the value of a control setting of the CRO. Now let's look at each option one by one. Amplitude is something that is related to the vertical distance and not the horizontal distance on a CRO especially. So A cancels out. Frequency could be true since frequency, as we know, is related to time period, and the time period of a wave can be figured out using the time base setting, if you recall. And the time base setting, as we know, is related very intently with the horizontal distance that we have on the screen. So this could be the answer. C is speed, and speed is something that sure you could calculate from a CRO, but it's not something you can evaluate from a horizontal distance or a display on the screen. So speed can't be it. And wavelength again, while yes, that might seem like the case since we're referring to horizontal distance, we have to remind ourselves that the distance that you measure on the screen has a different setting when you look at it with respect to the CRO. So the distance is not something you're actually evaluating from the horizontal display, especially the control setting. It's the time period that you're relating. So the best option we have is B. Next we have question 21. A longitudinal wave is traveling from left to right. The graph shows the variation of the displacement of the particles with distance along the wave at one instant in time. Displacements to the right are positive and displacements to the left are negative. Which labeled point represents a compression? Now remember, these are different points along the longitudinal wave, so it helps to draw them out individually. So if we look at point A, we see that it has a positive displacement, which means its displacement to the right. So that's A. B is a particle that has no displacement, and so it's momentarily not moving left or right. C is a point that has negative displacement on this graph, meaning it's displaced to the left. And then D has, once again, no displacement, and so it's not moving right or left. We want to locate a compression, and we remind ourselves that compression means that particles are moving in together or moving towards each other. They're bunched up close is what we mean. The one point where we see that waves or these particles are moving in together, that's the point B, because A and C seem to be compressing towards B. So B in that case is our best option that labels a compression. More specifically, it labels the center of a compression. Even though you might say the same for D, you can guess that if you look at the next point here, let's call that point X, it's moving away from D. So D is in fact labeling a rarefaction instead of a compression. So B is the only other option that's left, right? Next we have question 22. A source X emits a sound wave of constant frequency F. The wave is subsequently received at a stationary detector Y. The frequency of the wave that is detected by Y is less than F. What could be the reason for this? Now, here we can place X and Y like so. What X emits has frequency F, and what Y is receiving, Fy, is less than what F is receiving. Now, diagrammatically, when you draw this in terms of wavefronts, when you want to show a wave that has some set frequency, you'd show it with some spacing like this, right? Now, if Y is receiving a wave that has lesser frequency, that would mean that lower frequency would imply that what Y is receiving, basically Y is receiving fewer waves every second. So one wave here, after a long time, you'll get the next wave, after a long time, the next wave. So you can see how this can be achieved only if X were moving away. Frequency doesn't change upon diffraction or reflection, so A and B cancel out. If X were moving towards Y, then Y would have been receiving more waves every second. So there should have been an increase in F. So in that sense, C makes the most sense. Now we have question 23. A beam of visible light is in a vacuum. What could be the frequency of the light? So here you can solve this in two ways really. If you can remember, sometimes students like remembering the value or at least the order of frequency of light, which is 10 raised to the power 14 hertz. And you get here, with that in mind, you directly get option D. But sometimes students find it difficult to remember this order and instead can remember the range of wavelength of light, which is 400 to 700 nanometers or 4 to 7 into 10 raised to the power -7 meters, right? So if you remember the frequency range directly, you can easily evaluate option D. If not, you can use these frequencies. You can basically use these wavelengths. You can use the speed of light and then calculate frequency as the speed of light divided by wavelength. So you will get a maximum value for frequency and a minimum value. So let's suppose one value of frequency you get is 3 into 10 raised to the power 8 divided by 4 into 10 raised to the power -7. So here you should get 7.5 into 10 raised to the power 14 hertz. And then the second value you get -7, plugging this into your calculator, you get 4.3 into 10 raised to the power 14. So that's your minimum value. The first one you measured is the maximum value. So you basically pick any option that lies between this minimum and maximum. And that the only option is D. Now on to the next one. Here we have question 24. Now question 24 says, a vertically polarized beam of light of intensity I0 is incident normally on a polarizing filter. The transmission axis of the filter is at 45 degrees to the vertical. The beam of light transmitted by this filter is then incident normally on a second filter. The transmission axis of the second filter is horizontal. Now we're asked, what is the intensity of the beam of light after transmission through the second filter? Now, here it's a matter of successively seeing how intensity changes after each filter. One regular relation that we do know is that the outgoing intensity is related to the ingoing intensity and the angle at which you shift the filter by cos square theta, where theta is the angle between the between the axis of that filter as well as the vertical and the vertical. Now let's first see what happens due to the first filter, after the first filter to be precise, and I'll call this I1. Now I1 would be I0 times cosine square 45. Upon calculation, this gives you a factor of 2, half. Now the outgoing intensity or the direction of light that is being polarized, initially we had it as vertical, but then the outgoing light after the first filter will be tilted at an angle of 45 degrees due to the first filter's own tilt. So what's coming towards the second filter is angled like this. And since there's this 45 degrees and the total angle splitting here is 90 degrees, you can automatically calculate that there's a further angle between the tilted light I1 and the transmission axis of the second filter, and that angle is a further 45 degrees. So when you do calculate the new intensity I2 in relation with I1, the angle you will place is going to be an additional 45 degrees. So now it's just a matter of plugging in the values, half, and then what you get is I0 over 4. So the answer we should pick is option B. So here it's, even if the question doesn't show the angle strictly, you should be able to figure it out like this as well. It's just a matter of taking it step by step. Now to the next one. Here we have question 25. A stationary wave is formed by two progressive waves traveling in opposite directions along the same line of travel. Which statement about the two progressive waves is not correct? So if you want a stationary wave to be formed, you need complete constructive and destructive interference to happen. Constructive and destructive interference to happen. If there's any lead or lag between the two, interference. So let's see which option obeys this. Now, or follows or allows constructive and destructive interference to happen. With this in mind, actually, we can immediately cancel out option C, because C says they must have the same wavelength. If they do have the same wave, suppose if they didn't have the same wavelength, suppose this red wave was being overlapped with this green wave. With this green wave. They don't have the same wavelength. Even if they have the same amplitude, you won't see a complete construction of the wave, of the two waves, or a complete destruction, because there will always be points that have some non-zero amplitude that might not even be a maximum value. For this reason, this kind of an approach wouldn't work. So this is in fact correct, that they must have the same wavelength. So we want to pick an option that's objectively wrong, so C can't be true. For the same reason, they must have the same frequency is also a true fact. It's a true fact, because if they didn't have the same frequency, then even then you would have this kind of a situation that would occur, where waves with larger frequency would be bunched up closer, waves with smaller frequencies would be farther away from each other, and once again there would be the issue of incomplete constructive and destructive interference. So B can't be true either. And if they can't have the same, and since they should have the same frequency and same wavelength, they will automatically have the same speed as well. So D can't be true either. Automatically that means they must have a constant phase difference. And even this is true. Why? Because when you want constructive interference to happen, you need to have no phase difference. Whereas so here you would have the phase difference to be 0, And if there was a destructive interference happening, you would have a phase difference of pi radians. So it must change from 0 to pi alternatively for this process to occur. So it can't be constant. So A is an incorrect statement. Next we have question 26. The sound from a loudspeaker placed above a tube causes resonance of the air in the tube. A stationary wave is formed with 2 nodes and 2 antinodes as shown. The tube has a height 60 centimeters. The speed of sound is given. What is the frequency of the sound? Now the frequency of sound can be found easily from the frequency can be found from the speed itself by the formula for wave speed, that is speed equals frequency times wavelength. So frequency would merely be wave speed divided by wavelength, right? Now we know for a fact that we have the wave speed, but we don't have the wavelength. The wavelength can be figured out if we can basically simplify the number of loops and relate it to the length of the tube. So we can see here that we have 1.5 loop. So 1.5 loop or 1.5 loops over here. We also know that one loop has precisely half a wavelength in it, right? So if we had 1.5 loops, how many wavelengths would that be? Well, it's just a matter of cross multiplication. Let's call that x. We get lambda over 2 times 1.5 or 3 over 2, and we get 3 lambda over 4. So this represents the length of the waves, the length of the waveform presented here in terms of wavelength. Now this length, as we see, is equal to 60 centimeters, or in terms of meters that would be 0.6 meters. So now we can rearrange this to make lambda the subject of the formula. We get 0.6 times 4 divided by 3. 0.6 times 4 divided by 3. And here you'll get 0.8 meters precisely. So now it's just a matter of plugging it in here. 340 divided by 0.8. And what you get is 425 Hertz, which rounds off to 2 significant figures up to 430 Hertz. So our answer is A. Now on to the next one. 27 says, a continuous progressive wave, a water wave in a ripple tank passes through a gap in a barrier and diffracts. The width of the gap is greater than the wavelength of the wave, which change causes the wave to spread over a larger angle as it passes through the gap. When you're talking about a spread over a larger angle, you want more diffraction. To affect diffraction, you can either change the wavelength or the gap size. Only one of these two things can affect the diffraction. So frequency wouldn't change anything because that depends on the source rather than the point of diffraction. Height of the barrier will once again change nothing. So you're left with either option A or B. If you look at the situation, you're given the case where the gap is greater than the wavelength. So if let's say the red line that I've drawn is the gap, then these blue lines that I'll draw are the waves. The gap is larger than the wavelength currently. Now, if I decrease the wavelength further, I just bring the waves closer to each other. And that will ultimately cause an even lesser amount of diffraction, because the slit size and the wavelength are no longer comparable. But if I actually make the gap size smaller, then I'd be basically making the wavelength and the gap size comparable to each other. And so B is the only situation where diffraction can be greater, because only once the wavelength and the gap size are comparable to each other, only then can we have good amount of diffraction. Alright, next we have the diagram shows a view from above of a double slit interference demonstration. L is a monochromatic light source with a vertical filament. B is a barrier with 2 narrow vertical slits, and S is a screen upon which interference fringes form. The intensity is I at the point on the screen where the center of the fringe pattern is formed, so that would be somewhere here. I'll label that C. When one of the slits is covered, what is the intensity at the same point on the screen? Now we know that interference relates with the notion of waves overlapping, right? Now, for waves and when waves overlap, there will be an effect on amplitude. Now, we must then also remind ourselves that there is a relation between intensity and amplitude, that is, intensity is proportional to amplitude squared. Now, when both slits are available, that's when you have maximum amplitude. So let's call that A over here, right? Now, when one of the slits is covered, now we want to find the new intensity. When one of the slits is covered, at C, you'll only have one wave approaching the center. When one wave is there, the maximized amplitude that you had at the center basically is decreased by half. Because now there's only one wave interfering there. So it's not one amplitude plus one amplitude giving you double the effect. With just one wave, it's merely half of the amplitude that will reach here. So the new intensity is half of the original. Sorry, the amplitude is half the original, so the new intensity would be A squared over 4. And there's a proportionality between them. So you can see how the new intensity is proportional to half of the original. Or not even half, but rather it has a factor of 1 over 4. So it's a fourth of the original. So the one option that matches this is option D. Next we have question 29. Green light of wavelength 550 nanometers is incident normally on a diffraction grating and produces a diffraction pattern on a screen placed 3.5 meters from the diffraction grating. The third order maximum on the screen is a distance of 0.75 meters from the zeroth or central maximum. What is the distance between two adjacent slits in the diffraction grating? Now, here we recall the equation that we had ascribed to the situation of a diffraction grating, where we had d sine theta equals n lambda. D is precisely this distance between two adjacent slits in the diffraction grating that we wish to find. Theta is the angle of deviation between the central or the zeroth order maximum up to some nth order that we have. That is something we don't really have over here, but we can easily calculate. N is given as the nth order maximum that we're interested in, that's given. And wavelength is also given as 550 nanometers. So let's first figure out what theta is before we can even dive into figuring out what d is. Theta can be solved by resolving this right angle triangle that we have. And from here you can see that you have the side adjacent to the angle theta and the side opposite. The one trigonometric ratio that will work here is tan theta, which is opposite over adjacent. Taking the inverse on both sides, we can solve this, and with our trusted calculator, we arrive at a value of theta which is 0.75 divided by 3.5, tan inverse of this value, and you should get approximately 12.1 degrees. Now that you have theta as well, now we can easily figure out what d is. It would be n lambda over sine theta. Now we plug in the values. For lambda, we have to resolve this into its SI unit. So it would be 550 times the value of nano, which is 10 raised to the power negative 9. And then sine 12.1 degrees. So now it's just a matter of plugging everything in. And the value we get is 7.87 into 10 raised to the power minus 6 meters. Rounding this off to two significant figures, we get 7.9 into 10 raised to the power minus 6 meters. And so we arrive at C. Alright, that's great. Now moving to the next part. Now next question. Question 30 says, which charge can be carried by a charge carrier? Now, here we're relating charge with the elementary charge constant, which is Q equals NE, because we know that the only value of charge that is allowed is if it's a multiple of the elementary charge E. where E is 1.6 into 10 raised to the power negative 19 coulomb. Now with this in mind, what we need to verify in choosing which option will work is basically take the charge given in each option divided by the elementary charge and see whether you get a whole number or a whole integer value, a positive integer. Only then will we pick one of the options. Otherwise, if it's not a whole multiple of the elementary charge, then that is not a true charge carrier value we can allow. So let's see. If we look at option A, we take 1.1 into 10 raised to the power negative 19 and divide it by the elementary charge. Here you'll get 0.6875. Now this is clearly not something that you can round up or down. You want an exact value. So A can't be true. Let's look at B. When you plug in B, you get 2.5. Well, sure, this is a neater looking decimal, but once again, not something you can round up or down in this situation, so B is not allowed. But if we look at option C, here we get exactly 3, meaning C can definitely be the answer. And just to be sure, let's look at option D as well. Here you have 5.6875. Once again, not a whole number you can treat, so C is the best option we have. Next we have question 31. A resistor of resistance R is connected across a cell of electromotive force or EMF E and negligible internal resistance. Which single change to the circuit would lead to the largest increase in the power dissipated in the resistor? Now the one formula that relates internal resistance R and potential difference V in regards to the power dissipated, the one formula we have is V square over R. Since here there is only one resistor attached to one cell, the potential difference would be exactly equal to the EMF, so I can rewrite this as E square over R. So it's this equation that we wish to use to figure out which of these following changes will give you the largest value of power dissipated. So let's look at each option one by one. If we look at A, it says we're doubling the value of E. So the new power P1 would be 2E whole squared divided by R, which is 4E squared over R, which is basically 4 times the original value. P is basically me replacing E square over R wherever I see it. Now let's look at option B, doubling the value of R. If I double the value of R, I get E squared over 2R. This is nothing but the original power P decreased. So there's no increase occurring here, so B can be cancelled out. Let's see option C. If I half the value of E, I get E over 2 whole squared divided by R, in which case I get E squared over 4R. Now this produces an even larger decrease if you notice, because now it's fourth of the original power instead of just half. C also cancels out. Now on to option D, where we're having the resistance. So E squared over R over 2. We get E squared, 2 goes to the numerator, and here we see a doubling effect. So while A and D both show an increase in power, A shows the largest increase. So our answer is A. Now we have question 32. An electrical cable is made up of one thick strand of copper wire that is surrounded by 8 thin strands of copper wire. All 9 strands of wire are connected in parallel with each other. A cross-section of the cable is shown. Each thin strand of wire has cross-sectional area A and length L. For the thick strand, we're given 4A and length L. The cable has a total resistance R, and now we wish to find which expression gives the resistivity of copper. Now in this scenario, we want to basically find out the formula for resistivity, which we'll write here as a reminder, is resistance times cross-sectional area over length L. We can't use the total resistance here. We want to use the resistance of either the thin strand or the thick strand because we have information of area and length for both of them. But we want to first resolve this and figure out what the individual resistance of any one of these is. For this, we can use the concept of the total resistance. So let's take this step by step. Now here we want to find the total resistance R, where all the wires are arranged in parallel. Now for parallel, we know that the resistance would be basically a sum of the inverses and then a collective inverse, right? Now let me call the resistance of the thin strand Rs for the small wire, and for the thick strand, I'll call the resistance Rt for a thick wire, or the thick wire, yeah. So when adding these up, I have the inverse of the thick strand, since it's 1. Now you have 8 other thin strands, right? You have 1, 2, 3, 4, 5, 6, 7, 8. That much is given in the question as well. Now you have 8 of them arranged in parallel, each of them. So you'd basically have to add them up 8 times. Now of course you could continue this up to 8. I can make things simple, and of course there's a collective inverse as well. I can make things simple by just adding up the 8 inverses of the small resistance that I have as 8 over Rs. Right? It's just a matter of me adding up all the ones. Now I do have this, but I need to figure out any one of these values of Rt or Rs. In which case, I can recall the fact that these two wires are made up of the same copper wire, which means that the resistivity of the small wire is equal to the resistivity of the thick wire. I can use this formula to my advantage. For the small wire, I can write Rs times its cross-sectional area A over length L. And for the thick wire, I'd have RT times the cross-sectional area 4A divided by length L. Now it's just a matter of me cancelling out A, cancelling out L, and I realize that Rs is simply 4 times RT. So I can plug in this value of Rs into my equation for total resistance R. So I get 1 over RT plus 8 over 4 RT, a collective inverse. Simplifying things, I get 4 1s are 4 2s are 1 over RT plus 2 over RT. Resolving this, I get RT over 3. And so I have found the resistance of one thick strand of the wire, that is 3 times the total resistance. Now I have this for the thick strand of the wire. I have its cross-sectional area and its length L. Now it's just a matter of me plugging it into the expression for resistivity to find the resistivity of copper. Here I don't need to worry about the small strand, the thin strand, because it's the same copper wire. And so I get 3 times R times 4A over length L, and my answer will be 12 RA over L. The one option that matches this is option D. Next we have question 33. A car has sensors for detecting the light intensity and temperature of its environment. The sensors make use of an LDR and a thermistor. The car moves from a warm and dark environment into a cold and bright environment. What are the changes to the resistances of the LDR and thermistor? Now, here basically we have to remind ourselves of what effects do each LDR and thermistors have in regards to their resistances. Here we'll recall that for the LDR, there's an inverse relation with brightness, and with the thermistor there's an inverse relation. Okay, so one thing here, when I say LDR, I mean resistance of the LDR, and by the thermistor I mean the resistance of the thermistor. For the LDR, that resistance is inversely related to brightness, and for the thermistor, that resistance is inversely related to temperature. With these two factors in mind, let's look at which option makes sense. When you're going from a warm to a cold environment, the temperature is dropping, which would cause the resistance of the thermistor to increase. So we can cancel out options B and D, right? Now let's look at the first question. The scenario of the LDR. For the LDR, we see that we're going from a dark to a bright environment, which means that the brightness is increasing, which will ultimately cause the resistance of the LDR to decrease. And so C is the correct answer. Next we have question 34. A student assembles the circuit as shown. Which row describes the state of the two lamps? Now, here it's just a matter of seeing which of these paths will be forward biased and reverse biased, and then see which lamp will glow up. We remind ourselves that only in the forward bias setting will we expect current to flow through. So, I repeat, only in the forward bias setting, current will definitely flow. Whereas in the reverse bias setting, current will definitely not flow. So with this in mind, we'll basically follow the conventional current direction. So out of the positive terminal, at this junction, current will split. So let's first see what happens through lamp 1. Through lamp 1, you can see that the diode is indeed forward biased. So current will flow through and lamp 1 will definitely glow. So we can cancel out option A and C. Now let's look at what happens at lamp 2. At lamp 2, you have the current further splitting up. Along one path, the diode is forward biased because the current is entering the triangular base and leaving the vertical line. If it were the other way around, then there wouldn't have been any current flow. So no current flow here, yes to current flow in the first scenario. We see that one diode that we have on the left is forward biased, but the one on the right is not. But still the second lamp will glow. Why? Because you still have one conducting pathway towards the left that is allowing current to flow through uninterrupted. So even though you have one diode that isn't forward biased, there are two others that are. So lamp 2 will turn on as is lamp 1. The answer is D. Now on to question 35. Kirchhoff's first law is a consequence of the conservation of which quantity? Here we recall that Kirchhoff's first law states that the current going into a junction, total current that is, we can represent that total by using the sum notation. So the sum of current entering or going into a junction equals the sum of current going out of a junction. Current is a quantity, so there's no loss of current occurring, no gain of current occurring. Current is a quantity that is related to charge, and so charge is the quantity that's being conserved in first law. Now on to the next one. Question 36 states, 3 identical cells each have electromotive force or EMF E and negligible internal resistance. The cells are connected to 3 identical resistors, each of resistance R as shown. What is the potential difference across one of the resistors? Here we'll recall Kirchhoff's second law, which states that the sum of EMFs should equal the sum of potential differences around a closed loop. Here our closed loop is precisely the series arrangement given. So the sum of the potential differences can be easily calculated. Suppose one of the potential differences is V and they're identical, so they'll be the same amount for each of these. The sum would just be thrice times V. Now for the EMFs. Now the sum of EMFs is not that straightforward because we have to see how the terminals are arranged. So we see that for this EMF E, if we follow the conventional current direction, the positive terminal matches with the negative terminal, so there will be an addition of EMF here. But when you look at the next terminal, or when you look at the next cell, the positive terminal faces the positive terminal of the other cell. Now there will be a cancellation. So the sum of EMFs is actually just EMF E. So when you equate the two, you get E equals 3V, meaning V is going to be E over 3. So the answer will be specifically B, right? Now on to the next one. Question 37 says that in the potentiometer circuit shown, the reading on the ammeter is 0. The LDR is then covered and the ammeter gives a non-zero reading. Which change could return the ammeter reading to 0? Now, here we have to first ask ourselves or address the scenario of why is it that the ammeter reading is 0 in this situation? If you think about it, there's no interruption that's happening, right? So in this scenario, we remind ourselves that current is 0 when there is no potential difference. So if the ammeter is giving 0 over here, what that means is that the potential difference across these 2 points is equal to the potential difference across these 2 points. So let me call the upper one V1, the lower one V2. And in this scenario where the current is 0, V1 has been equal to V2. Now you have covered the LDR. So now the LDR basically, when you cover the LDR, you're basically decreasing the light intensity shining on the LDR. And if the brightness has increased, the LDR's resistance has increased. Now when the LDR's own resistance, I'll call this, has increased, when the LDR's own resistance has increased, the potential difference across the LDR will also increase because now it's offering more resistance than before. So if let's say this potential difference is V3, V3 has increased. Now, suppose the power supply has an EMF E. The EMF E is distributed equally across the first arm and the second arm, right? Because in parallel setups, the EMFs are distributed equally. But if you look at the first path, the EMF is split as V1 plus V3, since V1 and V3 themselves are arranged in series. So the sum isn't changing when you're covering the LDR, right? Because the power supply is still the same. So if V3 has increased due to the increase of the LDR's own resistance, V1 has to definitely decrease. So now V1 has gone to a smaller value than before. So the equality that was there before is now this. And it's because of this difference between the two that now there's a current that is definitely flowing. So if I want to bring the current reading back to 0, I wish to decrease V2. I repeat, we wish to decrease V2. The one way we can decrease V2 is if we decrease the resistance offered by the uniform metal wire, or specifically offered by the specific section of the wire, the one that I've mentioned over here, the one that I'm coloring right now. It's this we're including because it's the only one that's bounded by the sliding contact. We don't have to look at the point beyond the sliding contact. We're only looking at common points that are shared. Now, the resistance of this portion of the wire can be decreased if we were to decrease the length of the section itself, because we remember resistance is directly proportional to length. So the sliding contact needs to be moved to the left, which will cause V2 to decrease until the current reading becomes 0. So the sliding contact must be directed towards the left. That's the only option that works here, right? Now on to the next one. Now here we're in the last stretch. 38 is basically an application of the definition of isotopes. We know isotopes are elements with same number of protons but different number of neutrons. Right? With this in mind, we want different number of neutrons, so there's only one option that matches this, and that is C. Now on to 39. A neutron N is fired at a uranium nucleus. The neutron is absorbed by the nucleus, which then splits to form nuclei of barium and krypton. What is the number of free neutrons emitted when the uranium nucleus splits? So here's just a matter of constructing a nuclear equation and then seeing how things balance on both sides, right? Now, we are told that the uranium nucleus, proton number 92, mass number 235, absorbs a neutron, breaks into barium 56 and 141 and krypton. And then there are some number of neutrons that are also emitted. So let's call that X number of neutrons. Now here's just a matter of looking at the mass numbers and figuring out what X is. On the left hand side, the total mass number is 235 plus 1, 236. And on the right hand side, you have 141 plus 92 plus X times the one offered by neutrons, X. These have to be equal. So 236 equals 141 plus 92 plus X. Now it's just a matter of solving for X. So 236 equals 233 plus X. X would simply be 236 minus 233 equals 3. So the answer we should pick is option D. Now finally we have question 40, which says, that a pi plus meson has a charge of plus E, where E is the elementary charge. It consists of an up quark and one other quark. What could be the other quark in the pi plus meson? So in order to choose which one would be the true combination, we have to basically we have to solve this in terms of charge basically. So we can, even if we don't know what the other quark is, we can calculate what charge it will have. Because the charge of the up quark we know is plus 2 over 3e. For the other quark, we don't know the charge, so we'll call it x. The charge of the up quark plus the charge of the other quark should add up to give you plus 1e. So we have plus 2 over 3e plus x equals plus 1e. Making x the subject of the formula, we get 1 minus 2 over 3e. That will be plus 1 over 3e. If we look at option A, we have anti-down, which is the antiparticle version of the down quark. We remind ourselves that the down quark has a charge. It has a charge of minus 1 over 3e. So if we talk about the anti-down version, it will have a charge of plus 1e. Plus 1 over 3e to be precise. This matches this, and so the answer will definitely be option A. Alright, so I hope you were able to follow along this entire discussion, and we will go further into the theory paper right in our next video. Thank you.